A very good afternoon to everyone. In today's class, we will see about drone simulation using Matlab. So our main objective is to introduce Simulink, and we will import a 3D CAD model into Matlab Simulink with the help of Simulink Mechanics, and we will also design a simple system for quadcopter movements. First of all, we will see what is Simulink. Okay, so I will try to introduce Simulink to you. Simulink is a power simulation program that comes with Matlab. It is used to simulate wide range of dynamic systems. Simulink is a easy to use drag and drop environment for building simple and complex signal and system dynamic simulations. It allows the user to concentrate on the problem without worrying too much about the programming language. So if you are going to use Simulink, you need not know about programming. But when you are using Matlab, you have to program, you have to type in everything. But over here, when you are using Simulink, you are going to use only blocks. Okay, and Simulink is having n number of libraries. Out of those are sources, which include blocks that have only output, and sinks, those are the blocks that have only input. It could be a scope, and you have a continuous block, which is a block having an integrator or a transfer function. Then you have discrete blocks. These blocks will discrete transfer function or a memory. And then you have math operations like gain, product, sum, and trigonometric functions. And you also have user defined functions like S function and S function builder. So let us have a brief introduction about a quadcopter. Quadcopters are aerial vehicles which are operated remotely to fly independently. The control of vehicle motion is achieved by altering the rotation rate of one or more rotor disc, thereby changing its torque load and thrust to lift characteristics. Normally, quadcopter drones have 4 rotors. If there are 6 rotors, then it is called as a hexcopter. If there are 8 rotors, then it is called as a octocopter. For today's simulation, I am going to use a plus configuration quadcopter. Okay, over here in a plus configuration quadcopter, the opposite propellers will rotate in same direction. Okay, so that is over here we are having a front and rear propeller. They are going to rotate in a clockwise direction, and the left and right propellers are going to rotate in anti-clockwise direction. So this happens during the takeoff motion and also during the landing motion. During takeoff motion, the propellers, all the four propellers rotate at high speed, and during landing motion the propellers tend to rotate at low speeds. And for a backward motion, the rear propeller must rotate at high speed than all the three propellers. Over here, for a backward motion, the front propeller must rotate slower than the right and left propellers. And for a forward motion, it's just the opposite. Your front propeller must rotate in a high speed, and your rear propeller must rotate slower than the right and left propeller. And for rotation, if the quadcopter wants to move in the left direction, then the right and left propeller must rotate slower than the front and rear propeller. And if the quadcopter wants to move in the right direction, that is to the right of the horizon, then your right and left propeller must rotate faster than front and rear propeller. What we are going to do today is we are going to simulate the rotation of the propellers, and if the propellers are rotating, there will be movement for the quadcopter. We are going to simulate the movement of the quadcopter to make a lift and to make a right turn and a left turn. For this, we have to model a quadcopter in SolidWorks, and after modeling we have to convert the physical model, that is the quadcopter model, into an XML file. After that, we are going to import the XML file into Matlab Simulink. In Matlab Simulink, we will create a control system for the drone's movement. Now for the first step, we will assemble the quadcopter using SolidWorks. For this, I am going to create an assembly of quadcopter. The parts for the quadcopter were already modeled. So here in SolidWorks, we will import the solid parts. this is going to be a fastener, this is the propeller fan, and this is the model for brushless DC motor, and you have a nut. So this is a very simple model. Over here I am going to remove the fix from the nut. I am going to float it. Okay. So I am going to fix this stick 1. For this, right click on stick 1, click on fix. It will fix the part. And now we will make this hole with this hole. We will align the two holes. Okay, now the mates are concentric to each other. The holes are concentric to each other. Now these two surfaces, this surface and then this angle surface, these two must be parallel to each other. So both of them are now parallel to each other. Click on OK. Now we have to make a mate of coincident between this surface and then this surface. Okay, these two surfaces must be anti-aligned. Now it looks okay. Now we will fasten these two frames with one another. I am making concentric mate between the two circular surfaces. I am going to lock the rotation here. Our aim must be to make this assembly with only 1 degree of freedom, that is only rotation of the propeller fan. And over here I am going to push this fastener inside the frame by making the two surfaces coincident to each other. So next I have a nut. I am going to put the nut onto the bolt. So these two will now be concentric to each other. So over here also do lock rotation, so that nut must not be rotating. And here we will do a coincident again for the surface of the nut and the lower surface of the frame. Okay, and over here, as you can see, that the nut is inside the part. So for this, we are going to make these two surfaces parallel to each other. Okay, now we will assemble the brushless DC motor model onto the frame. So now these two are concentric to each other. Lock the rotation. Okay, the brushless DC motor must also be aligned with the frame's surface. I am making these two coincident surfaces. It was okay. Now we will insert this propeller fan over here. For this, I am going to make these two cylindrical surfaces concentric to each other. So these two are concentric to each other. Okay, and my propeller must be on top of this surface. Just zoom in, we could be able to see that surface, and then we can make those two surfaces concentric to coincident to each other. Okay, so like this we have to assemble other DC motor models and the propeller fans. For this, I am making copy of the propeller fans first. I need 3 copies. Press on Ctrl and drag on the object. It will create new copies. And now on the motor part. Press on Ctrl and create new copies of the DC motor. So it's just a model. Okay, Now we will insert the brushless DC motor on the frame. So now these two are concentric, and that too it must not be rotating, so lock rotation. And these two surfaces must be coincident to each other. So I am repeating the same steps, okay, to assemble the brushless DC motor model onto the frame of the quadcopter. Okay, these two are coincident now, and we will go for the last DC motor. The rotation must be locked, and give OK. Now click on the surface and rotate, and click on the inner surface of the brushless DC motor model and make those two coincident to each other. Okay, now it is okay. Now we will arrange the propeller fans onto the DC motor. So if you are not able to see the inner surface, so it's not visible here, so we have to move the model, move the fan just outwards by dragging it, and now we can create a mate between the fan and the brushless DC motor surface. So that to a coincident mate. Okay, now for the next fan, so I am arranging it as a concentric, so I won't be able to see this inner surface, so I have to move it just outside. I have to drag it and move it. Okay, now go to mate, now coincident between these two surfaces must be made. Okay, and next the last propeller fan must be assembled. Okay, so we are having the same problem. So we have to move the part slightly outwards by dragging the part, and now we will create a mate for the two surfaces, for this surface and then this surface as a coincident mate. Okay, so now everything is mated to each other. Okay, so we must be making sure that only the fans are floating. So this is a float symbol, only the fan is floating here, everything else is fixed to each other. Only the fans will be moving. So we have assembled the quadcopter model. Now the next step is we have to convert this physical model to a XML file so that we can import it to the Matlab. For this, go to Tools. Here you will be having SimMechanics, and export this model as a SimMechanics second generation, a newer generation model. So I'm going to create a new folder here. I'm going to save the model as Quadcopter .xml and save it. We all the parts into a STL file and the assembly to a STL file, and then converting only the assembly file to an XML file. Okay, so this will take about some 5 to 10 minutes. The XML file has been created. Okay, if there are any errors in your assembly model, then the errors will be shown. We have to rectify the errors, and then we have to convert the model to a XML file again. So here in the new folder, we have all the files. Okay, over here all the SLD part have been converted to STL files, and the quadcopter file is now an XML file. Now we have opened Matlab. In Matlab, first we have to import the XML file. So this is a command window where you have to type in your commands for the import, and I am going to change to the project folder. So the project folder is in my desktop, a new folder. So this is my project folder. Select that folder, and now you will be able to see the files in the folder. Okay, so now I have to import this quadcopter file into Simulink. For this, the command is sm import. Just type it, and now the file name must be within brackets and within these two dashes. So now type the name quadcopter .xml. So an XML file stores the data to be transported. It stores the data as a structured one. Now let the Matlab import the model. So till the time we will see about the Simulink blocks used. Okay, so we are using a Simulink block for our simulation. So it is my duty to let you know those blocks, what the blocks we are going to use to simulate the model for movement. First one, we are going to use a step block. So the step block provides a step between two definable levels at a specific time. Okay, so you are having two values, a lower value and a higher value, and the step block, what it does is it will step those values. Okay, so if the lower value is 1 and the higher value is 2, the step block will gradually increase the value of 1 to 2 with time. If the simulation time is less than the step time, the block's output is the initial value of the parameter value. For simulation time greater than or equal to the time step, the output is the final value. Okay, so the two definable values are initial value and the final value. And this is how we can give the input to the step block. First you have step time. The time is in seconds. When the output jumps from the initial value parameter to the final value parameter. Okay, it's the time taken for the value to change from the initial value to the final value. And next we have to input initial value. So it is the block output until the simulation time reaches the time step parameter. And next we have to give the final value. It is a block output when the simulation time reaches and exceeds the step time parameter. So next we have a gain block. The gain block multiplies the input by a constant value. Okay, so if a input is going to be a value of a, the gain block will multiply that value of a by a constant value. It could be a x. Okay, the input and the gain can each be a scalar or a vector or a matrix. Okay, over here we can give the parameter as the gain, how much times it must be gained. That value can be given as an input. Next we have Simulink PS converter block. So this block converts the unitless Simulink input signal to a physical signal. The default destination block units are meter, kilogram and seconds. You are giving an input, it is not having any unit. You wanted to convert that unitless input into a unit. So if you are inputting a value of 1, you don't know that whether it is a meter or centimeter or millimeter. If you want to give the value, that one value as meter, then we have to use this Simulink physical signal converter, which converts the input signal to the physical signal. Next we have 6 degrees of freedom joint block. This block represents a joint with 3 translational and 3 rotational degrees of freedom. 3 prismatic primitives provide the translational degrees of freedom, that is in x direction, y direction and z direction, and one spherical primitive provides the 3 rotational degrees of freedom, that is rotation about x, rotation about y and rotation about z. You will be having a single spherical primitive which could be rotating in all the 3 directions. At each time step during the simulation, the joint block applies the sequence of time varying frame transformations in this order, in the following order. At first it will do for translation along the x-axis of the x prismatic primitive, and then along the y-axis, and after that along the z-axis. Then only it will be simulating the rotation about the 3 axes x, y and z. So the model now is imported. So this is how a quadcopter looks like in Simulink. We are having blocks. Okay, so a stick is a block here. So it is the frame of the quadcopter. So if you go in that, you could be seeing that it's a solid body. Okay, it's a solid. And over there in SolidWorks, we have made mates. Those mates, they have been taken here as joints. Okay, for example, a concentric mate is a revolute joint here. And we are having the fans here, that is your propeller fans, which must be made to move. Here you have one, there is one, 2, 3, and the last one is here, 4. So we have to give torque in these revolutes if we want to move this fan. If the fan must be rotated, we have to give torque in these revolutes, which are connected to the propeller fans. So before that, let us see whether the model is imported perfectly. For this, just press on run. So it will compile here. So it is compiling. And you can see the model in the main window. Okay, we have our model here. Right. So the 4 propellers are here, and your frame is also here. So the model is perfectly imported to the Simulink. First, over here we have to identify where is the propeller 1. For this, double click on the fan block. Over here you will be having the propellers block, and over here click on solid and go to graphic. So what I am trying to do is, I am trying to change the color for the propeller. So I am going to give a green color for this propeller. Okay, and go back to the quadcopter, and now press on run. It will compile again. So this is my first propeller. So I am going to fix to a front view. So in this view, this is a propeller at the front. Okay, so here. Now what is fan 2? So this is to control the fans. So I'm going to give the color as this blue for the second fan. And for the third fan, I'm going to give the color as yellow. Okay, so and let the fourth fan be red in color. So these are all the fans. Okay, so the first one is green, second one is blue, and the third one is yellow, the fourth one is red. So let me make a note of this. Now at first we will join a 6 degrees of freedom between the world and the transform. Okay, so the world block is the block which provides the ground frame. Okay, it is going to be the environment. And next we have the solver block. So no need to change any solver configurations for this model. And next we have a mechanism configuration. Over here, if we want to have the effect of gravity, we can have the effect of gravity. Okay, this is your gravity in x direction, this is the gravity in y direction, and this is the gravity in z direction. So I don't want to include gravity. I will delete that value minus 9.81 and give the value as 0. Click on OK. Now we have to include new blocks. For this, press on library browser. It will populate all the blocks which are available in Simulink. This is the Simulink library browser. Over here, search for degrees of freedom blocks. It will populate all the degrees of freedom blocks. We need 6 degree of freedom joint. So it is here. Just click on it and drag it onto your Simulink. Okay, now we have this 6 degree of freedom joint, and we need the 6 degree of freedom joint between the world and the transform. So for this I am going to delete this link. So just select the link and click on delete. Now for making the link between the world and the 6 degrees of freedom joint, just click over here and drag a line onto the world line. And for joining the transform with 6 degrees of freedom joint, just move your mouse, dragging it, and now we have 6 degrees of freedom joined to the Simulink model. Next, we have to give torque for all these revolute joints. Okay, so all the revolute joints which are connected with the propeller fan. So double click on the revolute joint, go to actuation. Over here we have torque, it is now none, that is 0. Change it to provide by input and click on OK. So now we have an input here. Likewise, change here also for all the revolute joints which are connected to the propeller fans. So the revolute joint is a joint acting between two frames. And where is the last one? Last one, fan is here and the revolute joint is here. Double click on the revolute joint. So double click on it and go to actuation, change the torque to provided by input, click on OK. Now we will import step block from the library. And after that, import the gain block. And after that, we need PS converter. Okay. Here we have Simulink PS converter, not the other one. Okay. So now we will give the input values for the step block. I am going to give the step time as 0.1 and the initial value as 0 and the final value as 1, and click on OK. And now connect this step to the gain and connect the gain to Simulink PS converter, and after that take this converter to revolute 5 which is attached to fan 1. Okay. Now we will try to simulate it. Let us simulate it. So it will compile. Go here. You can see only the fan number 1, it is rotating. So it is rotating in anti-clockwise direction. Okay, so that fan number 4 also must be rotating in anti-clockwise direction, and fan 2 and 3 must be rotating in clockwise direction. So over here we are having the motor rotation in clockwise direction for the front and rear. So if we want to change the direction, click on gain and give the value as negative. -1 will now rotate the fan number 1 in the opposite direction. Okay, it is now rotating in clockwise direction. Now we will try to add 3 more gains. I'll move this gain here. Okay, and we will also have Simulink PS converter for each gain. So for this, just click on control and drag your block. It will create a copy of that block. Okay. So this is getting cramped over here. Okay. Now from this step, gain to the Simulink PS converter, and from the converter to the revolute. So the fan 2 is going to be the fan on the left side. It must be rotating opposite to this. So the gain value must be a positive value. Okay. Now from this gain 2 to step, and from now connect this gain 2 to this PS. So here we are having a link, so I have to delete that link to have this link attached to the physical converter. Okay, and now this physical converter must be connected to the fan number 3. So the fan number 3 is also having a rotation same as fan number 2, which is on the right side. So these two must be positive. And now from step to gain, okay, and now gain to Simulink, okay, and now PS3 to the last fans revolute, okay, and this value must be negative, okay, and now run your Simulink model. Now you can see that fan number 1 and fan number 4 are rotating in clockwise direction, and these two propeller fans are rotating in anti-clockwise direction. Okay, so we are seeing it from the back view. If we are seeing in an isometric view, we can see the lift of this quadcopter. For this I am going to slow it down, okay, and change the view to isometric view. So maybe the speed is not enough here, so we have to increase the speed, we have to increase the value. So we will increase the value by 1000 in each gain. So where is gain number 1? It's here, minus 1000, okay, this is going to be plus 1000, and this is going to be also plus 1000. Gain number 3 for the last fan, it is going to be minus 1000, okay. So what I am doing is I am increasing the RPM of the quadcopter's propeller fan. So it is getting computed here. Yeah, we haven't defined the solver settings, that is why it is not working. So let us define the solver settings. So we have to start the simulation from a steady state, and we can use a local solver like backward Euler equations, and we will give apply and OK. So now compile it. Go here. So as you can see here, the quadcopter is lifting up, It is slowly lifting up. Okay. And now we will try to simulate the other movements. So for our next movement is backward motion. For this, the rear must be having high RPM and the front propeller must be having a lower RPM. Okay, here fan 1 and fan 4 are front and rear propellers. So the fan 1, it is connected to the gain here, so it must be going slower. So I am giving a value of -500, and fan 4, and fan 4's revolute is here. And it must be given a gain greater than the other two fans which are in right and left side. So I'm going to give a value of 1500. Okay, so let us see whether it works. So I'm fixing the back view and trying to run the compilation. So it will take some time for us to see the movement. And as you can see that due to the variation in speed of each of the propeller fans, a torque is induced in the quadcopter itself, okay, which is trying to pull the quadcopter backwards. Okay, now let us see in the isometric view. It is trying to go up also due to the thrust produced by fan 2 and fan 3. And now for the next motion. So the next motion is the forward motion. So over here we must interchange the values. So for gain this must be 1500, and then this gain 3 must be 500. Now compile the Simulink model. Go here. So let us see from the back view first. Okay, the model is starting to move now. So that is how we can. So the next motion for our model is the left turn. For this, the front and rear must be moving faster than the left and right. So this must be having a lower value. So let us say it is 500, and gain 2, it must be also a lower value, 500. So we will reduce it. Okay, we will reduce it to a very lower value of 1, and over here also reduce it to the value of 1, and so gain 1 must be 1500. Okay, and for the last propeller it must be also 1500. So it is okay. Now stop it. And compile it again. So it was running in the background. So as you can see here, it is slightly drifting towards the left side, while going up. So we are viewing it from the back view, that is why. So it is now drifting towards the left side. So front view is showing a good result. And now for the last movement. For this movement, the left and right propeller fans must be moving faster. So we have to stop this. So the left and right are fan 2 and 3. And where is fan 2? Fan 2 is here. Fan 2 is here and the revolute is here. For this, the gain, it must be greater. So I'm going to give a value of 1500. And for fan 3, the gain is here, so it is also 1500 in a positive way. And for gain 3, the value must be too low, so I'm going to give a value of -1. And for the first fan, the gain must be -1. Let us simulate it. So we can see the drift here towards the right side. So that is how we can simulate a quadcopter using Simulink. So this is a very basic Simulink model. We are having models for environmental models are there, and there are also models to create an actual quadcopter with batteries and ECS and there are many models available online, and you can use your quadcopter design which is made in SolidWorks or in ProE or in Creo, and we can use that model, and we can also simulate that model in an environment. So if you are trying to navigate an quadcopter and you are trying to place an autopilot system in it, it is possible by using Simulink. You can simulate how a quadcopter is working in real-time environment. So I will show you an example of that. So let me open that example. So it will be having many blocks. So this is a quadcopter simulation done by Matlab themselves. So over here we can download this code. It is free of cost when you are registering with Matlab, and after that we can just remove their model and input our model, input your new model, and you can simulate it according to the real-time environment. So the project file is here. So on the model I am trying to open is the complete quadrotor model. Which is being controlled by actuators, roll, pitch and yaw. So this is the model developed by MathWorks. So here you can see that they have developed sub-assemblies, and inside sub-assemblies we are having controllers. Okay, so this is a PID controller which is trying to control the altitude of the quadcopter, and next we have a roll, pitch and vertical state of the controller, vertical state of the quadcopter. So these values are given as a command for the motor. And you have an actuating mechanism which is going to act as a torque, and for the ground stop we are having a different block, a sub-assembly block. And for external forces, so it could be a force due to some sudden changes, they are including that also, the environmental conditions. So then they are including sensors here. So they are including body state sensors and altitude sensors, and navigation sensors are also used here. So they are trying to navigate it through an environment through autopilot systems. So in this session we have seen a drone simulation using Matlab, that too Simulink. So we were introduced about what is Simulink and its libraries and the working principle of motor rotation, that is the fan rotation in quadcopters, that too plus configuration quadcopter. So and we have modeled a simple quadcopter in SolidWorks, and we have also converted the model into an XML file, and that XML file is imported into Matlab Simulink, and we have created a movement control system for the drone. So we have created how the movement is taking place in a drone, a basic movements like going up and turning right and turning left. And we have also seen the Simulink block used in this particular session. So we have used step block, gain block, simulation PS converter block, and 6 degree of freedom joint block. And we have also seen an real-time example which is developed by MathWorks. So if you are having any doubts, you are free to ask. I take this opportunity to thank our HOD sir, Dr. Kandal sir, and my colleagues, Mr. Balaji sir, Mr. Babu sir, Mr. Akhil sir, and Miss Kashmira ma'am, and also the lab assistants, Mr. Bansode sir, Mr. Upade sir, and Miss Poonam ma'am. And I also thank our clerk Sachin Gaurav sir, and also our Akshay for providing me the support to handle this class, to handle the session. And I also thank our VC sir, registrar sir, and director sir, and also the management for giving me the opportunity to handle a session in the ISTE sponsored 5 days online STTP under the title Design Development of Drones and its Application. I thank everyone and the participants for listening to me. I hope this session would be very helpful for you in designing a drone and its dynamics. Thank you.